Welcome everyone. My name is Oliver Kaas and I'm an advisor for internationally mobile researchers at the International Scholars and Welcome Office, a subdivision of the Business Unit of International Affairs at Karlsruhe Institute of Technology. It is an honor to welcome you today to the second edition of the International Excellence Talk series at KIT. After the presentation, we will have a Q&A and also room for discussion. Before we dive right into the presentation of Humboldt Research Awardee Professor Pelinovsky on rogue waves in nature and integrable models, we will hear a few welcome greetings. Now I hand over the floor to Dr. Petra Roth, the Deputy Head of International Affairs and the Head of the International Scholars and Welcome Office, for your introduction and welcome remarks.
Good afternoon. I'm pleased to give you a brief introduction to the event. KIT is one of the 11 universities of excellence in Germany, and our award-winning concept focuses on enhancing top-level research and the complete range from fundamental research to application. Strengthening international collaboration and promoting interdisciplinary networking is one important key aspect. That is why KIT established the International Excellent Grants and Fellowships Program, a highly flexible instrument which enables researchers at KIT to straightforwardly invite outstanding international colleagues for short-term stays into their groups. The intention of the International Excellent Talks is to provide a platform for networking by bringing together researchers and students of different disciplines and backgrounds, as well as interested persons, for informal exchange after listening to insights given by a distinguished researcher. And we would, of course, have been more than happy to have invited you to an in-person meeting and afterwards have an informal get-together, having some drinks and food together. So the international talks are presented alternately by International Excellent Fellows of KIT and by Humboldt Fellows and Awardees. For this, we gladly coalesce with the Humboldt Regional Group, Karlsruhe Pforzheim. And so we are especially happy to today welcome Professor Dmitry Pelinovsky, Professor of Mathematics and currently with McMaster University, Hamilton, Ontario, and a Humboldt Research Awardee expected to come to KIT in January next year. Professor Pelinovsky, we are pleased and honored that you are joining us today and are very much looking forward to your talk and to thought-provoking discussions afterwards. Professor Pelinovsky, who has an impressive international curriculum, will be introduced in good form in a few minutes by his host at KIT, Professor Michael Blum. Before I pass the word to Dr. Erik Bründermann, who will speak on behalf of Humboldt Regional Group today, let me thank my colleague Elena Pfeiffer, of course, Oliver Kaas, and Hanna Müller and Corinna Zülker for organizing and supporting today's event. Oliver, Hanna, and Corinna will be glad to take your questions in the chat. Dr. Erik Bründermann is head of the Department Accelerated Research and Development and Operations with the Institute of Biophysics and Technology at KIT, and he is a Humboldt Fellow himself. Dear Erik, the screen is yours.
Welcome everybody. So I'm also very happy to be here and to represent the Humboldt Regional Group, Karlsruhe Pforzheim. So I also like to welcome today Professor Dmitry Pelinovsky and his host, Professor Michael Blum, and also obviously all the Humboldtians in the audience and all participants in the name of the German Humboldt Club, which in German name has Deutsche Gesellschaft der Humboldtianer e.V. So if you participate in the opening of the annual meeting of the Humboldt Foundation yesterday, you have heard that the funding for most Humboldt fellowships comes from the German Foreign Ministry, and it is proven that the Foreign Office supports the building of personal ties and scientific bridges across country borders. So you also find the Humboldt alumni associations in many countries. If you look them up, for example, at the Alexander von Humboldt Foundation's website, you find 109, including 3 transnational associations located in 73 countries. So, which also includes Germany. So there are about 3,000 Humboldtians in Germany. So for example, myself, as it was mentioned before, and also those Humboldtians who already live in Germany. So however, it took until the year 2007 that 11 Humboldtians actually founded the German club at the university in Kassel. So at this point, I also like to mention that our spokesperson of the regional group, Karlsruhe Pforzheim, Dirk Wenzel, also one of the 11 founding members, regrets not to give this speech, welcome speech here, because he had another appointment, unfortunately. While we had the strong support by the Humboldt Foundation, we then founded several regional groups in Germany. And the group here in Karlsruhe-Pforzheim was founded 10 years ago by Dirk Wenzel and colleagues. So nowadays we have about 21 regional groups with more than 300 members. So all those who are funded or were originally funded by the Humboldt Foundation, either if they were coming from a foreign country and stayed here, or for example, in my case, I went to a Humboldt Awardee. So like today, Dmitry Pelinovsky is one of those awardees to another country and to do research at their research place. So I also invite you and also others Humboldtians, so if you're in an area in Germany of the regional groups, please do not hesitate to contact the local speakers, and we strive to support really the Humboldt family locally. So this can stretch from informal to formal meetings like today, but also visits, for example, to museums or hiking to include the whole family of an Humboldtian. So also in light of today's speaker, so we are also strive for excellence in our Humboldt Club. So for example, the treasurer of our organization who looks after the money is a mathematician. So I think that's probably a good sign. Our auditors is Dirk Wenzel, so our local regional speaker. He also chair in economics in Pforzheim. So Pforzheim is also a city close by in Karlsruhe and often called the jewelry and gold city, famous for its silver and goldsmiths. So if you have a chance, then if you're here as a visitor and can visit this other city, please do so. So let me conclude. In 2021, there are already 12 scientists from 7 countries who received the Humboldt Fellowship to work at KIT. In addition, we can welcome now Dmitry Pelinovsky, who is the only Humboldt Award winner at KIT this year. And I also noticed that in time, we probably could have met even earlier in the same space in the early 1990s in Nizhny Novgorod. So therefore, I'm looking forward to your presentation. I'd like to welcome you again. So please visit us in the network and ideally soon in person. For example, we can show you around at KIT or in the city, or even just to meet for a coffee in the canteen. So with that, I conclude my contribution here and I will look forward to the presentation and give back to Oliver Kahrs.
We will hear now the scientific foreword by Professor Michael Plum from the Institute of Analysis at the Department of Mathematics at KIT. Professor Plum is the academic host of Professor Pelinovsky in the frame of the Humboldt Research Award during his research stay at KIT.
It's a great pleasure for me to introduce Dmitry Pelinovsky a little bit from the scientific point of view. So he is one of the world leading experts in wave propagation. And wave propagation is in turn an important area of applied mathematics. Well, waves are everywhere in nature and also in technology. And it's remarkable how Dmitry combines physical intuition and numerical simulations and a large variety of mathematical methods to achieve his results. And these have amounted so far to around approximately 200 publications in scientific journals, plus a number of textbooks. And these have citations of a number of citations, which is in the thousands. So I think all over the years, there are around 8,000 citations. And many of these publications, by the way, were real breakthrough results, which makes it not so surprising that they have so many citations. And he is also active as editor in various journals, various very renowned journals, and remarkably not only mathematics journals, but also in very responsible and key positions in physics journals. In addition to that, he has received a tremendous amount of awards and honors by various international organizations, among them, for example, the EPSRC and the London Mathematical Society in Britain, or the CNRS in France, the NSERC in Canada, and many more. And of course, there is Humboldt, and he is already an experienced Humboldt guy. He received a Humboldt Foundation Research Fellowship in 2005 with 2 follow-up visits even in 2011 and 2015. And at that time, he did that with Guido Schneider in Stuttgart. And that was a very fruitful collaboration and was the basis of many papers. And I think also of one of Dmitry's textbooks, which I mentioned a bit earlier. And besides this Humboldt Research Fellowship, of course, there is now the Humboldt Research Award. And this is connected, as you have heard already, with intended visits to the KIT. for 6 months in the next year, and also to Stuttgart to Guido Schneider for 3 months. So we met some years ago on a conference in England. So Dmitry and I met in England, and then we did some joint work. And then the idea came up to nominate him for the Humboldt Research Award, and that also Guido Schneider was involved in that. And then, okay, we did it, and we were successful, and that is the reason why we are meeting here today. And we are, of course, hoping and convinced of many fruitful months when Dmitry visits the KIT. Last but not least, I want to mention that Dmitry's expertise on wave phenomena intersects strongly with the interests in our collaborative research center, so Sonderforschungsbereich, on wave phenomena, which is the same title, so to say, wave phenomena, which we have in our Faculty of Mathematics in KIT since several years now. And so wave phenomena on both sides. On that I'm very sure that there are many, will be many cooperations between Dmitry and members of our CRC, not only with me, but also with many others, in particular also with younger people. And I'm very much looking forward to this cooperation. So I think that's enough. So we are all waiting for Dmitry's talk. So let me stop here and hand the floor over to Dmitry, and I'm looking forward to your talk.
Now, with no further ado, I'm handing over to Humboldt Research Awardee Professor Pilinovsky, who will talk on rogue waves in nature in intangible models. Professor Pilinovsky, the floor is yours.
Okay, many thanks for welcome and for introduction. First of all, I would like to say that I'm delighted to accept this Humboldt Award and to attend this online conference. I look forward to visit Karlsruhe starting January next year to keep working with Michael Plum and also to engage in the new collaborations possibly in Karlsruhe and continue some of the collaborations elsewhere in Germany. So I'd like to talk about a little bit of my research, analysis of nonlinear differential equation and applications to different phenomena in nature, particularly in physics. And one particular research subject I'd like to talk today about, it's rock waves, which are very common in the ocean. So let me start with a general rough definition of what rock waves are about. Rock waves appear from nowhere and disappear without any trace. They are also known as the killer waves, freak waves. At the conference this week, I learned that they are also called in Taiwan mad dog waves because they bite like mad dogs. So many different names, and if you click on this link in Wikipedia, then you will see lots of documentation of rock waves in the ocean, documented by marine engineers. I would like to show some of the pictures in the first part of my talk, and then talk about mathematical models which can be used in order to describe such rock waves in the second part. So let's start with the general pictures of rock waves. In particular, I will start with the quotation of Homer, the Odyssey. The rock waves have been very well written and described in the literature. So Homer wrote, Poseidon, shaker of the earth, drove on a great wave that was terrible and rough, and it curled over and broke down upon and scattered abroad in every direction. That was one of the very first literature observation of rock waves. Let me give a physics definition of what rock waves are about. Physicists, marine engineers, they have stations across oceans in different places, and they observe water elevation. So here is a typical recording of a water elevation with the typical rock waves. If you can see the average wave which is observed over a period of time is about 3 meters high or something, but then all of a sudden from nowhere it appears a gigantic wave with an amplitude of 9 meters, and it potentially be very risky for ships, for oil refinery stations, for if it appears near lakes, near seashores, then it could hurt some civil objects on the shore. So physicists give a definition that if the wave exceeds double magnitude of the mean wave, then it is classified as a rock wave. Such events are very rare, but they could be devastating. And for example, some of the recording shows that ships could be destroyed completely by rock waves. So this is an event happened in South Africa with a world glory. A double-humped rock wave elevates the ship, and because of some goods they were carrying in the middle, it was very heavy. It was just completely broken in the middle. So here is another observation of rock waves from a ship. Observers were saying that the waves were on average 15 feet, maybe 4 meters high, not exceeding. And then all of a sudden, 3 gigantic waves came with a 17 meters high. Hopefully everybody was survived on this ship. This picture shows a very interesting shape of the rock wave. It's a so-called pyramidal wave observed some time ago. This is another observation from a ship. As you can see, the amplitude of the wave height exceeds the size of the ship, and so it is very dangerous for the ships. So this is another old evidence how the waves can destroy ships if they appear. And these are more recent observations with some catastrophe, some ships which were actually destroyed. An old picture where the upper deck was destroyed by a gigantic wave. So as I mentioned, marine engineers have been observing water level elevations in different stations and have been recording rock waves from time to time. So in this observation, what I would like to bring into the display, the relative magnitude of the rock wave compared to the average background. If you can see that the average wave has about 3 meters high, the rock wave comes with the amplitude of 9 meters high, which makes a triple magnification factor of this rock wave compared to the average wave. And this is quite interesting, whether it's universal or not, we will see later. Here is another observation, probably these are more like periodic waves or periodic rock waves coming from the cyclone glory. But this is another observation in the Black Sea. And again, we can see that the maximal height of the wave before the rock wave was not exceeding 3 meters high. And then all of a sudden, the rock wave comes with a 9 meters height. So again, triple magnification factor. So here is a connection to Germany, German Space Agency, which was monitoring the equatorial Atlantic Ocean. And here it's a record of a rock wave with a magnification factor to be 2.9 observed here. So as mathematicians and applied mathematicians, we would like to understand the phenomenon. We would like to use nonlinear differential equation in order to predict the phenomena, explain the phenomena, and analyze the phenomena. So here is a model which has been used for ages as a descriptions of a water wave on a deep surface. It's a nonlinear generalization of the famous Schrdinger equation derived long ago in the context of quantum mechanics. Turns out to be quite a fundamental equation which has many other applications in fiber optics, in waveguides, in lasers, in plasma physics, but in particular it has these applications to ocean. And so the very simple solution of this equation we can see. It's a so-called constant amplitude solution given by exponential of IT with a unit frequency. If you take, because psi is a complex varied function, if you take modulus of this, then it's going to be just uniform constant 1. Very simple solution. In fact, this very simple solution is just a model because this is an envelope of a quasi-harmonic wave. So with a constant amplitude, it becomes a constant amplitude wave background, harmonic wave background in real physics in the ocean. But for the mathematical model, it is simply described by this very simple equation, simple solution. And then Peregrine in 1983 found other exact solutions to the same nonlinear Schrdinger equation. In particular, he found this solution, which is given by a rational function multiplied by the same complex exponential function. It's an exact solution of this mathematical model. And what is interesting about this exact solution is that if you look at the space and time going to infinity, then this second factor in the rational function decays to 0, and the amplitude goes to 1. So in other words, the actual dynamics of this solution happen to be localized both in space and the time. And this is a fundamental rock wave modeled by nonlinear Schrdinger equation. Even more interesting, if you look at the magnification factor. So if the background has an amplitude normalized to be 1, then the wave reaches maximal value at the origin in space and time, and the maximal value is exactly 3. So it's a triple magnification factor. That's how the wave, the rock wave, can be displayed within this model. As a solution surface, we can see triple magnification factor. So if a ship is located, say, in the origin in the coordinate space, then the typical wave magnitude is about 1, but then all of a sudden from nowhere, it's a gigantic wave of a triple magnitude, which can potentially destroy this ship. So what mathematicians do, they study exact solutions of nonlinear differential equations and try to connect these exact solutions with possible applications in ocean dynamics. So in fact, this rational solution is expressed by a polynomial of degree 2 with respect to the special variables. It's the first solution of this sort. In fact, there is a whole hierarchy of rational solutions of nonlinear Schrdinger equation, which are given by polynomials of a high degree. And the next one in the hierarchy, so-called second order rock wave, is given by polynomial of degree 6 with several free parameters. And typically, this solution describes 3 individual rock waves of a triple magnification factor. However, there is a degeneration in the parameter space when this triple wave can merge together and form a rock wave of magnification factor 5. It's an interesting event. It's of course very rare event, even if rock wave is already rare. So it's a double rare event when the second order rock waves can be observed. But nevertheless, this can be simulated in experiments, and nevertheless, such rock waves are possible. So as I mentioned, there is a hierarchy of solutions. So this example shows third order rock waves, which is given by polynomial of degree 12. And typically it represents 6 rock waves formed in a special triangular pattern. And when again all parameters are degenerate, this rock wave just becomes isolated. This is a single event of a magnification factor 7. Besides simple constant amplitude solutions, nonlinear Schrdinger equation has many other solutions which are also responsible for more complicated wave patterns on the surface of the ocean. Besides simple constant amplitude solutions, nonlinear Schrdinger equation has many other solutions which are also responsible for more complicated wave patterns on the surface of the ocean. In particular, in my research, I was studying so-called standing wave solutions, which are periodic with respect to the spatial coordinates. And here are the 2 examples of the periodic standing wave solution. They are expressed in terms of so-called Jacobian elliptic functions. One Jacobian elliptic function, dn, is positive definite, and it's a generalization of the constant amplitude wave solution, which is shown here in a space, and this is a Fourier spectrum of this positive noidal wave solution. And the other elliptic function, Cn, or cnoidal elliptic function, is a generalization of a trigonometric cosine. This is sine indefinite solutions here with the spectrum to be only present on the odd harmonics. So again, these are exact solutions of the nonlinear Schrdinger equation. Nonlinear Schrdinger equation is already a simplification of the actual velocity fields, elevation, height of the fluid. So this periodic waves for NLS corresponds to quasi-periodic, more complicated wave pattern on the surface of the ocean. And in numerical experiments, different physics groups, in particular a group of a famous physicist Vladimir Zakharov, observed rock waves which may happen on more complicated wave backgrounds. So here are the numerical experiments involving exactly noidal positive definite periodic waves. In numerical experiments, I observed a single rock event of the magnitude factor 3 and a more complicated second order rock effect of the amplitude, which was close to 5, but not exactly 5. And they were thinking that maybe these events are very similar to what Peregrine found, to these rational solutions which exist in the Schrdinger Equation. That's where our group came into work, and we found exact analytical solutions for these rock events, rock waves on the standing periodic wave background. We developed so-called an algebraic method, which is useful, which is based on integrability structure of the nonlinear Schrdinger equation. And with this algebraic method, we obtain an exact analytical solution for such rock waves. With analytical solutions, we can compute magnification factor exactly. And with analytical solution, we can think about applicability of such solutions. So this is a series of papers with Zhenbin Chen from Nanjing, University of Nanjing, and also involving some of my students at McMaster. So here there are two examples of rock waves on the noidal positive definite background. One rock wave has a magnification factor between 2 and 3, depending on the nonlinearity of the background, and this would be classified as a rock wave. We were able, with our algebraic method, to obtain another second exact solutions for the rock wave phenomenon, fully localized in space and time on a background. However, the magnification factor is between 1 and 2, so physicists would not classify it as a rock phenomenon. But in mathematics, we can obtain these results and state that there are exactly two fundamental rock waves existing on this noidal background, and we can construct more complicated hierarchic solutions, but this would be much more rare than these fundamental rock waves. We can do the same with the conoidal background to obtain exactly one rock wave which appears here, and this rock wave is quite remarkable on a conoidal background. With the use of our of our algebraic method, we can prove that the magnification factor is exactly 2. And with a second order rock wave here, the magnification factor is exactly 3. So these are exact solutions of nonlinear differential equation. And the question is how interesting these solutions for physicists, for experiments, for marine engineers, for applications. So in fact, when our research was published, 2 experimental groups were immediately excited and started to produce experiments trying to capture these rock waves on the standing periodic wave background with not numerical, but a real physical experiments. One group is a group of Bertrand Kibler in Dijon, and they were doing experiments in optics. On the left, you see what they observed in, I think, with lasers. And on the right, you see just the results of numerical simulations. And so on a periodic standing background, there is obviously a self-focusing and some rock waves which appears from nowhere, disappear without trace. And this is quite similar to what we have as exact solution. And then another group of Amin Chapchuk in Sydney produced hydrodynamical experiments in water tank. And by the way, this is another connection to Germany. Amin did his PhD in Hamburg, and he's now a professor in the University of Sydney. So again, in blue, you see the real pictures of experiments in water tank. He was recording water elevations in a distance from the water source. And in the red, you see results of numerical simulations. And again, we see some focusing on rock wave, which appears on the background, on the wavy background. So one important mathematical question which we can ask, and which is still related very well with physical phenomena, is how rock waves are originated. So what is the main reason why rock waves are formed on backgrounds, on different backgrounds? And in fact, physicists knew, or physicists proposed it for a long time, that rock waves arise due to modulation instability of the background. So I would like to overview a little bit on what modulational instability of the background means in applications to these standing periodic wave solutions. So in fact, we would follow here the famous proverb of engineers: be wise and linearize. So what we would like to define as a stability analysis is first step to add a perturbation to the wave background, and then chop your nonlinear differential equation at the linear terms, and then study linear evolution of the perturbation. That's called linearization. So here on a standing periodic wave background, we have perturbation here, which depends on spatial and temporal coordinates. However, because the background, after we have taken away the harmonic factor in time, is independent of time, and because of this structure, we can separate the variable for the perturbation, and then reduce the linearized problem to the spectral problem, for which we would identify admissible values of the spectral parameter lambda. So here lambda is the growth rate. If we can find an admissible solution with a positive real part for lambda, then it means instability, in fact, linear instability, exponential growth of the perturbation on the standing wave background. And now let me give a mathematical definition of modulation instability. Since the background is periodic, we can consider perturbations, W's here, to be also periodic, with the same period when n is 1. But we can also consider long period perturbations with a multiple period where n is an integer. And then the limit of n going to infinity is the limit of a very long perturbation, or perturbations which could be even localized, not periodic. So what we define as a modulation instability is the existence of a sequence of eigenvalues for each n, where n is large but finite, such that the eigenvalue has a positive real part. So in other words, modulation instability, it's an instability with respect to the very long perturbations of the periodic background. If there exists a sequence of such unstable eigenvalues for every large but finite n, then we say that the background is modulationally unstable. Usually in the limit, when n goes to infinity, real part of lambda goes to 0, and this is how we can identify modulationally unstable backgrounds from modulationally stable backgrounds. So in connection to the two standing periodic waves, I have shown here the stability spectrum in the linearization of the nonlinear model. So here is a noidal background with positive definite periodic waves. We see most of the eigenvalues allocated on the imaginary axis, with no real part. This would be just neutrally stable modes which do not grow in time. However, there is one particular band which is located along the real axis. And so if we fix the multiple period of the perturbation n, then we get one eigenvalue here. And when we change this value of n, we will get a sequence of eigenvalues, all with positive real part. And this sequence converges to the origin on the plane. So in other words, we can identify modulationally unstable backgrounds by looking at the stability spectrum and trying to find an instability band which intersects the origin, like here's a real segment. For the cnoidal wave solution, again, most of eigenvalues are on the imaginary axis. However, we have this figure 8 band, and this figure 8 band intersects at the origin. So again, this determines modulational instability of the cnoidal background, Again, if you take a sequence of multiple periods, then we will have a sequence of eigenvalues along this figure 8. So my claim, my statement is that the rock waves we were able to construct by using algebraic method are related to the existence of modulational instability of this periodic wave background, standing periodic waves. And as an illustration of this main claim, I'm showing a more complicated standing periodic wave, which is a mixture between noidal and cnoidal wave. And the instability picture includes two figure eights. One is a very large figure eight, and for this very large figure eight, we can construct with algebraic method and a precise rock wave solution with a magnification factor somewhere between 2 and 3. But then there is a very thin figure eight, the inner unstable branch. And for this inner figure eight, we can also construct a very similar rock wave solution. However, this rock wave solution is delocalized in a space-time coordinate. So it is not an event which appears from nowhere and disappears without trace. This event, this rock wave, was brought from infinity as a propagating wave. It could still be devastating, however, it is more predictable because if people know it on the other side of the oceans, then they can predict that this rock wave will reach along this trajectory. If you know the speed, if you know everything, then we can predict when it exactly comes. So such a wave would not be classified as a rock wave. It would be called a solitary wave. And that's what it is, a solitary wave on the standing periodic background. So the conclusion out of this particular example showing that modulational instability generate or is related with rock waves, but if the background is stable, like in the case of this very thin wave in figure 8, then it's not a rock wave, but a propagation of a solitary wave on the background. I will finish my talk with another example of the same sort. And this example is given by the sine-Gordon equation, which is also a fundamental model, maybe not applicable to waterways, but applicable to, say, Josephson junctions in superconductivity. It's applicable to crystal dislocations in solid-state physics. And it is also one of the very important mathematical models and nonlinear differential equations, which can be solved by using what we call integrability tricks or integrability tools. So this is also a nonlinear model which is integrable with many conserved quantities. So if you look at the traveling wave solutions propagating with the speed c, then we can quickly identify that both supersonic and subsonic waves can be all generated from solutions of the famous model studied in undergraduate physics and well as undergraduate differential equation courses. It's a pendulum model. And as we know from mechanical example of a pendulum, it has two equilibrium points. One is a down position, which is stable. That's the origin on the phase plane, which represent all solutions of this pendulum equation. And the other upward position is unstable, which is here represented by a saddle point. So on a phase plane, which is a plane where we record all possible solutions as orbits, as level curves of a certain energy function related to this equation, we can see clearly that the stable equilibrium point is surrounded by bounded curves, which represent periodic orbits, and periodic orbits represent periodic wave solutions of the sine-Gordon equation, while the unstable points are connected by so-called heteroclinic orbit. And heteroclinic orbits separate two kinds of periodic motion. The one inside the heteroclinic orbit, it's called librational solution. It's sign indefinite, and it's in fact given by the same cnoidal function I showed before. But then outside of heteroclinic orbit, it's so-called rotational orbits when the pendulum simply rotates. And these rotational orbits are sign definite and they're represented by sigmoidal periodic wave solutions. So if we are to study these two standing wave backgrounds, it's actually here in this particular context, they're not standing waves, they're traveling wave backgrounds. But from the point of mathematical analysis of this equation, they work in the same way as the standing wave for the nonlinear Schrödinger equation. And so if you look at this two wave background, then we can perform stability analysis, which has been done quite recently by several different groups. And then for the rotational background on the left, we will see a very interesting picture, which is called instability bubbles. The origin is stable. There is just a vertical segment here. But for away from the origin, there are two unstable bubbles here. However, since they don't intersect the origin, we would say that rotational waves are modulationally stable. So if you look at the sequence of perturbations with multiple period, it will be just located around the origin and it will be stable. But perturbations of a short period, of a much shorter period than the period of the periodic wave, would be unstable, and so this is not an instability with respect to long period perturbations. So again, rotational waves would be modulationally stable. Librational waves, pictures on the right, are modulationally unstable because of this figure infinity band. There is also another unstable band, like a big circle band, but the other one is not related to modulation instability, just instability, but there is a modulation instability here because of figure infinity. And so, if we use algebraic method, construct rock wave solutions, will we see a difference which would just represent the difference in the modulational stability analysis? Let's do the rotational waves first, which are modulationally stable. Use our algebraic method, construct solution, and then we get a soliton. Not a rock wave, a soliton. In fact, we can get two fundamental solutions like this. This would be just two counter-propagating solitons. But now let's take librational background, which is modulationally unstable, and use algebraic method, generate new solution, and then all of a sudden it's a proper rock wave, which appears from nowhere. And in fact, this is fundamental rock wave, also shown here by different authors, but then one can construct a second order rock wave, which is generally represented by this triangular pattern of 3 rock waves, and we can generate the whole hierarchy of high order rock waves. But this time, this hierarchy of rock waves exists on the non-trivial traveling wave background. So these examples, I hope these examples will convince you that the claim I'm making has some good solid ground on connection between rock waves and modulation instability. It's not a theorem yet, and in fact, it's something which I'm still working on to prove this connection in a more general, in a more abstract setting rather than the settings of some toy problems. So this brings me to the end of my talk. Just to conclude, rock waves occur commonly in nature. I was mainly showing pictures in oceans. There are similar rock wave events which are known in fiber optics, in communications, and which could be devastating for optical communications. But here I was showing just real waves in the surface of ocean. And then I hope I convinced you, at least in my first example of nonlinear Schrödinger equation, that such events could be described by integrable nonlinear models like nonlinear Schrödinger equation. And for this, for these integrable models, we have developed methods which allows us to construct rock waves exactly, to compute magnification factor exactly, and to study relations between rock waves and modulation and stability, also by using rigorous mathematical analysis. And I will be very happy to take any questions if you have. Depends on what group are you in. So if you're on mathematicians studying nonlinear PDEs, then I would say that immediately when you destroy integrability, you destroy the existence of such solutions. But if you're in a group of, say, physicists, applied physicists, then they would say that no matter what perturbations they include, they still observe these individual rock wave events. And even real physical experiments which were made, it was not based on the models, it was based on real physics. And in these real optical experiments or in water tank experiments, people observed these rock wave events. And obviously, if you would just model it very accurately, not with idealistic equations I was talking about, but with perturbed models, we would not be able to get the exact solutions for this, for this rock waves. However, they truly exist. And moreover, if the perturbation is small, the magnification factor of these real rock waves is quite close to the magnification factor of the theoretical rock waves, of the exact solutions. And this motivates us to chop the model, get rid of the perturbation, and try to model it with integrable PDEs and find exact solutions. Of course. So as I showed, there are several exact solutions of the nonlinear Schrödinger equations. They are so-called rational solutions. And the first fundamental rock wave is just given by a polynomial of degree 2, and it has magnification factor 3. And so if, say, this platform would survive until triple wave magnification, then it would survive. However, there is a second order rock wave, which is given by a high order polynomial of degree 6. And generally, so it has several parameters. Generally, it is represented by 3 individual rock waves. And when they are distant from each other, they affect the platform in the same way as 3 individual rock waves. But when they're close to each other, the magnification factor is actually exceeding 3. And in fact, the maximum magnification factor for this triple wave is 5. And that's a mathematical result, which can be shown just based on the exact solution. And so if it is a rare event with 5-fold magnification, then that could be an explanation for the reason why the platform didn't survive. Obviously, there is some kind of upper limit for the wave it can. So the first question is about applicability of the nonlinear Schrödinger equation. For this, I can say immediately that originally, nonlinear Schrödinger equation was defined as a paraxial approximation in optics. And in fact, some of the physicists in my hometown, Nizhny Novgorod, like Talanov, Ostrovsky, they were very active on the derivation of this paraxial approximation. But then, around 1970s, physicists working with ocean, with surface waves, with internal waves, they started to derive formally nonlinear Schrödinger equation as the main model, simplifying evolution equations to describe real dynamics of ocean waves. And then mathematicians started to work, including my late colleague Walter Craig, who justified this approximation. So one of the results he did in his PhD was a justification analysis of the nonlinear Schrödinger equation for the water waves fluid. So therefore, NLS, nonlinear Schrödinger equation, is a well-justified models on all levels by mathematicians and statistical theory on the predictions. And sometimes people study statistics by using nonlinear Schrödinger equation, but sometimes they study it by using statistical models of rare events. For this one, I'm not so familiar with, but I heard some talks about both on statistics of rock waves and just a statistical type of predictions of rock waves.
Thank you, Professor Pilinovsky, for your very interesting presentation.
Thank you very much, Professor Pilinovsky. And this to you, it's only water, but cheers. Nice to have you with us.
Yeah, also from my side, thank you very much for a very interesting talk. So very interesting. So in case you're coming to KIT then next year, so please give us a call. And if you want to also see something at the large scale facilities or Campus North or Campus South, we're happy to show you around.
Thank you very much also from my side, Dmitry, and just want to repeat that I'm looking forward very much to see you next year in person.
Definitely, it was a pleasure to give a talk and to meet you all online. And so I hope that I will be able to meet some of you in person. And indeed, some of the collaborations with physicists, I'm always look forward to it. So when I was on sabbatical in Sydney, I gave a talk on rock waves, and then Amin came from civil engineering department, and then he was so excited that he immediately started to do experiments which resulted in the publications and physical reviews.
Thank you, Professor Pilinovsky, for your scientific contribution in our second edition of the International Excellence Talk series. We will hear our next International Excellence Talk on July 22nd with Professor Antonia Pirotta from the University of Palermo, Italy. So have a wonderful day and evening on whatever side of the Atlantic you are on, and hope to see you next time. Thank you and goodbye.
Okay. Goodbye.
Tschüssi.